Alright, so we got one more attempt here. And I'm unfortunately going to plug in my headset here because it's dying. Needs some juice. I think after this we'll go to sleep. So the plan is, this is an interesting one. The plan is going to be to attempt to validate a binary search tree yet one more time. So we already got almost 99%. It's pretty good, but that's kind of just random. But let me delete this. As you can tell, I've already got the solution from just a few moments ago. Earlier, I want to see if I could do this in like a few minutes. So, given the root of a binary tree, determine if it is a valid binary search tree. Valid BST is defined as follows. Left subtree of a node contains only nodes with keys less than the node's key. Right subtree of a node contains only nodes with keys greater than the node's key. Both the left and right subtrees must also be binary search trees. So 1, 2, 3 is a binary search tree. 1, 5, 3, 4, 6 is not, because 3 is greater than 5. All right, so what we can do is, there are a few ways to solve this, but we're going to use what's called a Morris traversal, which we're going to thread our binary tree to not use any extra memory than what's already given to us, and then we're going to traverse the tree, and we're not going to terminate early because what we need to do is an in-order traversal, so we're going to print each node sort of left to right, as if in-order traversal is we process the left subtree, then the root node, then the right subtree, and we do that recursively. Excuse me, but we're going to use an iterative approach called Morris traversal, which involves threading the tree, which basically causes the leaf node's right pointer to point up the tree back to sort of to where you came from, quote unquote. It's a bit vague. It's not exactly that. It's kind of special how you thread it. We're going to thread, and we're also going to process the nodes and unthread simultaneously. So we're going to thread, process our in-order traversal, and unthread all in one shot. And we're going to do this in order to perform Morris traversal on our binary search tree. And if all the nodes that we process, if every pair of nodes, the previous and the current node, if all of them are in ascending order, all those pairs are ascending, then we're in good shape. Then we have a binary search tree. If any of those pairs are flipped or off, and we don't have a binary search tree. And we have to be very careful here to not terminate early, because we might have threads in our tree. So here we go. Here's what the Morris traversal might look like. And it really has only 3 pieces to it. It has the initial current node, so the root. Then there's a previous node, which should be the null pointer. Then we just, as long as we have a current node, we're going to update the previous to the current, and we're going to set current to the right. And the 3 parts, we're going to say Boolean threaded, so we're going to say in-order Morris traversal. Morris traversal to ensure that the traversal ascending, strictly ascending, monotonically increasing. Otherwise, the tree, binary tree, is not a valid binary BST. Okay, so we have a Boolean ret equals true. If we get all the way through, we'll return ret. If we see any problems, we're going to set that to false, but we are going to continue to make sure all of our threads come out. So first we want to have a threading check to see if current is threaded. So we'll say if current, we're going to say if current left exists. Then we're going to check that subtree to see if we're threaded. So the way we're going to do that, we're going to say for, we have a loop here, and we're actually going to break on a certain condition, and unthread, and set threaded to true. Yep, and we also we'll call it R, I'll show you in a moment what that is, and unthread, and it's going to be tree node R is going to be current left. Let's start off at that point. As long as R right exists, we're going to continue to update R to R right. So eventually what's going to happen is this should go all the way down to the right side, all the right nodes, and stop at the bottom right node. And then now if that bottom right node, it's not actually not necessarily stop there. It could be a loop. If it's threaded, it's actually going to keep, it won't loop, the last jump will be actually our current node. So that's the condition we're looking for, is the next jump. If the next jump is to the current node, then we know we're threaded. We move the thread. Move any threads, and don't thread if if current node, don't add threads. Current node is a previously threaded node. So now if we're threaded, if we're not threaded, no threads are found. It's not a previously threaded node. Sure, I thread all of the left nodes down to the leftmost node from the current node. So we're going to say, so there's a double loop here. And we're going to say this actually doesn't have a, oops, oh, wait. I don't know what I just did. I think there's something from the local cache. I think I just printed what was in the local cache. So tree node R is we're going to say current left, if it has something, then we're going to update to the left side. We're going to set R is going to be the right node of the left tree, and we're going to say, actually it's going to start off at the left, excuse me. So it's on the left. So if the left subtree exists, we set R to that left subtree. We're going to move, as long as R right exists, we're going to update R to R right, and then we're going to set R right to current. So we actually move current down the left side, and what we do is we pick the rightmost node of the left subtree will be threaded up to the current node, right? So we take the left subtree, we take R, set R to start at that point. We traverse R all the way down until we hit a null pointer, until there's no rightmost node to go to, and then we set our rightmost node to the current. So we thread back up that way. And finally, process each node here. And here we're going to say if previous and previous value, if that's greater than or equal to the current value, then we're going to say red equals false. Super simple thing here. And that's it. That's the whole Morris traversal for validating a binary search tree. And that should be correct in general. There you go. Done. Hey, pretty good. Now that took us almost 10 minutes. Not too bad. By the way, you can use this Inorder Traversal for any related binary search tree question. So the other question that we looked at earlier was if we find two places where we need to swap the nodes in our binary search tree in order to to put the binary search tree back into a proper binary search tree. There were two nodes that needed to be swapped. Very similar question to this one, and obviously we had a similar answer before. It's actually why we got into all of this, so that way I could do both of those. So this is a very, it's linear time complexity, but it's also constant extra space. So yeah, thanks for watching, and talk to you soon.